Yes, thank you, Jerry, helping out remotely here. Cool. So today's lecture is going to be essentially like a guest lecture. So I'm going to cover like some interesting applications of some of the stuff we've been learning over the last few weeks, specifically in computer vision. So I'll introduce like some concepts in there. Well, this is like for my work. So yeah, think of this as like a guest lecture basically. But I did want to go through like a couple of things from last time, and there are a few announcements. So project 3 due Friday, homework 12 due Wednesday, and then last lecture is also Wednesday. So again, our lecture on Friday. So you guys basically made it to the end here. So we're almost done. Office hours today, 4 to 6 p.m. at FSM. So please stop by. And we have these course evaluations out. You may have received an email about this. So please fill this out. Looks like we've already had quite a few people fill it out. But try to get your friends to do it in the class. If 50% of the class fills this out, then everyone will get 3 extra credit points on the final exam. So please tell your friends to do it. Basically fill it out and like tell 2 other people in the class to do it, and then tell them to do the same thing, and like you'll guarantee success. So yeah, so please do that. Cool. I believe you guys can do this. Last semester they succeeded to get the 50%. So all right, any questions about any of that? Cool. All right. So a few things I wanted to just review really quickly towards the end of the last lecture. We didn't really get to cover this. So just quickly go through this and then we'll move into like the guest lecture part. But basically, we talked about how we can build this classifier. We built all these sequences of functions. At the end, we were able to basically like classify and make an actual prediction on like what class do we think this new example is in. And the last step is usually to evaluate the accuracy of your classifier. And so the way that you'll typically do that is you take your data and you split it up into a training set and a test set. And the way that we do this is right here with this line of code. So first we just take everybody in our data set, we sample the entire table with replacement equals false, because we want to randomly just shuffle all the rows. So this is very similar to the shuffling that we did when we did A/B testing. So you just want to shuffle everything, basically just like randomize the rows, and then take like the first, in this case, first like 342 rows. That's our training set. And then the remaining rows, I'll go to the test set. So that's just like one way you can shuffle, or one way you can assign things to training and test. And the reason we just do the shuffling is because if I just go take the first 342 rows, they might be sorted by something. They might be sorted alphabetically or some other value. We don't want to do that. We don't want them to be sorted anyway. So we just got to shuffle them up first. And then once you've split up your data set into training and test, then we go through and actually evaluate the accuracy. And so the way that we do this is we made this function called evaluate accuracy. And what it's going to do is it's going to go through our test set. So that's one of the arguments to this function. It's going to drop the class from the test set. So it's going to say, let's assume we don't actually know the outcomes of our test set. And then let's just go through one by one for every example in the test set and just classify. So make a guess on what we think this model is going to predict for that particular individual in the test set. Once we have that classification, we're basically just checking whether the classification is actually equal to the actual outcome that this person had. So we actually know what they had because we have the full data set for that test set. And if it's equal to our prediction, then we increment this value that we're tracking called num correct. And this basically just like adds up. So it starts at 0, it goes through the loop, each iteration basically like checks if we got the guess right. If we did, increase num correct by 1, essentially. That's what this line is doing. It's like this is going to be either equal to 1 or 0, depending on whether the guess is correct. And then at the end, you should have, once you're out of this loop, you have that the num correct is the number of predictions you actually got correct. Just divide that by the total test set size, and you have your evaluation accuracy. So that's pretty much how that code works. So yeah, any questions about this code? Okay. Yeah, so this is pretty important. Like we want to make sure that we're evaluating on this independent data set that's not actually like taken into account when we built our model. So our model is all built based on the training set. Those are the set of people that we consider for our nearest neighbors. The test set's just like independent set of data that we're going to evaluate on and just see how things work. And so if you actually go through and evaluate, we kind of went over this last time, but you can see how the accuracy actually varies. And you can go ahead and like change up the number of neighbors if you want to try something else. And in general, in most of machine learning, and we'll talk a little bit about this today too, you have to kind of like tweak these parameters on your own. The value that you choose, the best value that you find is going to change depending on the problem, depending on the data set. There isn't usually like some guidance. One thing that we do for nearest neighbors is we're going to be picking an odd number. The reason for that is because we want to make sure there's no ties. So, if I pick like 4 people to consider as my nearest neighbors, if 2 are in class 0 and 2 in class 1, I have a tie. So if I choose an odd number, it kind of guarantees I'm not going to have a tie. So that's why you'll see we're always trying odd numbers here, 5, 3, 11, 1. If you look at the past exams, that's what we're doing as well. So that's really important to remember why we choose the odd number. Cool. Any questions about like classification in general that I could answer? Yeah. Yeah, exactly. These 4 cells are testing which number of neighbors is going to be the most accurate on the test set specifically. Yeah. Yeah, is the only way to do that manual trial and error? Essentially, yes. So, you'll typically have like a grid of values, like an array of values that you're going to like try. And you'll probably see at a certain point, like once I get to like 21 neighbors or something, it's not getting any better after that. And so we don't even worry about going beyond that, but you'll typically just try like a grid of values. And someone brought up, I think it was after last lecture, they said, could you use like a minimize function? Could you make a function and try to minimize it to try to find the optimal K? You could maybe try that too. The main thing with K is like, it's going to always be an integer. So when it's an integer, right, these values can only be 5, 3, there's no decimal options here. You usually don't use minimize or something like that. You can just kind of iterate over some values. Minimize is typically for something like a slope and the intercept where the value could be anything. It could be any real number. And so that's where minimize is more useful. But you could probably make your own function that kind of does what minimize does under the hood, and maybe kind of tries a bunch and then returns the one that's the best. So you could definitely try to do something like that. It would be pretty cool. So what exactly does the classify function do? The classify function basically says, take this example from the test set, find the K nearest neighbors. So let's say K is 5, find the 5 nearest neighbors in the training set, and then look at what class appears most often among those 5 neighbors. And then that's what we return as our prediction. So it's just like how to make the prediction. And it's, we kind of over that a little bit more last time on how we find the nearest neighbors, but that's pretty much how it works. Cool. Awesome. All right. So that's classification. Actually going to talk quite a bit about classification today. So yeah, for today, I basically wanted to go over some examples in prediction. A lot of this is from my work. So I previously worked in like autonomous driving, so I'll share some examples in there. And then now I have a startup in sports doing something very similar using computer vision, using images. So I thought I'd talk through a little bit about how some of these models are made. A lot of this is going to be kind of beyond the scope of the class, so I'm going to try to just simplify it quite a bit here. And feel free to stop me at any time to ask questions. And I think there's some interesting learnings from some of these projects that apply to like any sort of machine learning or prediction type of problem in any domain. So it's not just going to be specific to images, but I'm hoping to give you guys like a little bit of an introduction to how machine learning works with images and how we process it, which I think is a really cool field and is being applied to a lot of different domains. So firstly, some review. So this is going to feel like review from the last few weeks. But in general, when we're trying to make predictions, the way we'll do it is, let's say we have some numerical value, such as midterm scores. We're trying to make a prediction about something else, such as final exam scores. And if you make a plot of them against each other, you might see a scatter plot like this. And so, one question you might ask is, let's say I know I got a midterm score of 80. What's my final score going to be? Can I make a prediction of that? And so a reasonable way to do this is to look at your scatter plot, draw a line through the center. Looks like it's kind of moving in the same direction as most of this cloud of data. And then just go up from 80 to where this line is. And that's like a reasonable way to make predictions. So we've kind of talked about this already, right? And so you can actually, any line you try to draw through your scatter plot, you can formulate it like this. So, Y in this case is the final exam score, X is our midterm score. And so you can formulate it by saying that our predicted final score is going to be some slope times the midterm plus some intercept. And so this is just a way you can formulate any line. And so we kind of went over this a few weeks ago. And then the question is, of course, yes, I can draw a line through it and it looks like it's going through the center, but how do I know that's the best possible line? I need to find the best possible line that's going to give me the best possible predictions throughout my entire data set. And so, any of these lines all look like they're kind of going through the middle of the scatter plot, they all seem like they could be kind of reasonable, but the predictions are very different. So if you look at where 80 is, of course, the predictions vary so much. This line over here puts our final at the exact same score of 80. This one up here puts our final score above 90. So like personally, I'd probably prefer this line for myself if I got an 80, but like that doesn't mean that's the best line. We have to make sure this line's like working well for everybody. And so how do we find the best line? Well, one way we can do this is we can say, okay, if we have some line that's being considered, we can look at a particular example. We'll typically call this the training example in the world of machine learning. And we can evaluate what the prediction would be for that example, just go straight up to the line, that's the prediction, and then calculate the difference, it's the training error. So we've been calling this like residuals, same thing. In machine learning, we'll typically call this a training error. So it's just the difference between what the line predicted and an individual example. And then you can go ahead and calculate that for everybody for this entire scatter plot. And you can summarize that with a single number. We talked about this as well, right? Mean squared error. So that's how we can sort of summarize how well a particular line is doing. And once you can do that, basically what you've done is now you can take any line that somebody proposes and just give it a score of like how good it is. And you want to basically find a line that's going to minimize that score because that's the best possible line. It's the one that's making mistakes the least. And so that's kind of how we typically find the best line. And so if you're using kind of the classical statistics approach, you can just use the regression equation that we gave you. So we can you can just use this equation. Like we know the optimal line is going to be where the slope is equal to the correlation times the standard deviation of y divided by standard deviation of x. And the optimal intercept is like the average of y minus the slope times the average of x. So we had this like formula, we can just plug it in and we're kind of guaranteed to get the best possible line. But in machine learning, what you would typically do is you'd go through a process where you start by picking out a random slope and a random intercept. So you pick some random values. We don't really know like which values are going to work. Then we calculate the training error across our entire data set. So we like make predictions, calculate the training error. Then we adjust the slope and the intercept a little bit and then see what happens to the training error. Does it improve? And if it does, let's just keep adjusting the slope and the intercept until it stops improving. That's essentially how most of machine learning works. And so this is basically like how pretty much every AI type of model that you're seeing today, ChatGPT, whatever, DALL-E, they're all kind of made the same way. Obviously, there's some more complexities and I'm really simplifying a lot of the math here, but that's basically what they're doing is like, you're just picking an initial slope and intercept, trying out how it does on your scatter plot, and then adjusting the values, trying it out again, and then keep adjusting until like you don't get any better in the error. And so when you're working with just like a simple straight line, there's no need to do this bottom piece here. You don't need to do any of this because we already know we're guaranteed that this is going to give us the best possible error. So when you're just fitting like a vanilla straight line, this is the best possible one. You shouldn't waste your time like going through this process. You don't need to do that. The reason you do have to do it is if the equation for your prediction is more complicated. So if you have like, imagine you have like a lot of inputs. I'm not just considering my midterm score. Maybe I'm considering like several different inputs. So maybe I have my midterm score and there's like a slope for that, but then maybe I also have like prior coding experience and there's like a slope for that. And then I have like how much chocolate I had that week. There's a slope for that. And then I have like how much exercise I had the night before the final. And so you could imagine that you could start to make your equations more and more complex, add more and more inputs, and each input is going to have essentially its own slope. So that's kind of how it starts to develop if you add like additional things into your equation. And so when you have things like this where it starts to get like more and more complex and you're doing weird stuff like you're using like a log or a sine or some other fancy math stuff, then what starts to happen is that you're not going to be able to necessarily find like a straightforward solution just using an equation. You're not going to have something nice like this where I can just plug it in and I have my answer. It's not necessarily going to be that case. So as you start to get like more complex equations, which most of today's machine learning is doing, you're not going to be able to just find like a simple solution like that. You have to go through that iterative approach of like try out some values, see how the prediction works, adjust the values, see how it works again, keep going. So that's kind of how most machine learning works today. And so generally we'll kind of just write this whole equation more generically as just like, it's some function of like a bunch of slopes and a bunch of inputs. That's basically how we write it. And so it's just like a simplification of the equation. And so if you can write in Python, a function that has a bunch of slopes and a bunch of inputs, then you can use something like the minimize function we talked about to find the optimal value of the slope. So that's typically how it will actually work in machine learning in actual practice. And so you can kind of just plug this into the minimize function and it'll tell you this is the best value for the midterm slope, this is the best value for the experience slope, and so on. And you'll just get all your values back out. And that's the one you should use for your predictions. So that's pretty much like how we would actually practically find the best predictions with this sort of an equation. So any questions about that so far? Okay, cool. Sweet. So let's talk about images. So here's a picture of a really cute dog. And so let's say I wanted to build a more complex classifier where the input of the classifier isn't just going to be like a few different numbers, it's actually going to be this entire image. So I just want to pass this image into the classifier. And then I want to output whether this is a dog or it's fried chicken, right? So imagine like I wanted to make that as a like classifier. So how would I do that? How would I even approach this problem? What does this data look like? Is this numerical? Is this categorical? What is this? So let's actually zoom in to the dog's eye. So this is what it looks like if you zoom in. And you can actually literally do this like on this image. This is straight up from this image. And so if you zoom in, you see all these little squares. So these are pixels. So these are pixels on your image. And so what are pixels? So it seems like these are different categories because like I have some black pixels, some white ones, some gray ones, some brown ones, some different variations of brown. So it seems like these might just be like categories, but actually they're numerical. So each individual pixel essentially has 3 numbers attached to it. And if you've done anything in like Photoshop or like Illustrator or any sort of like graphic design, you're probably already familiar with this, but basically every pixel is actually just 3 numbers. And the numbers correspond to kind of like the amount of red, green, and blue. So typically call them RGB. And so your computer knows that like this combination of these 3 numbers gives you this like slightly brownish color. And then it knows that like these combinations of pixels gives you this slightly grayish color. So your computer knows to like convert those numbers into this like image and these colors, and that's how it presents it to you. But really under the hood, all we really have here is just numbers. So every pixel is 3 numbers. And if this is like a 1080p image, let's say, so 1920 by 1080, that's going to be 2 million pixels. So 2 million pixels in one image, and then times 3 numbers. So it's like 6 million numbers. That's basically what this is. It's just 6 million numbers. So that's a lot of data. And that's just one example, right? When we go back to like training examples in our scatter plot, you can think of one dog, one image as like one point in the scatter plot. So now all of a sudden, each point has 6 million data points in it. So it's a very large input size that's going into your model. But now I kind of have a way to think about this. So it's like, okay, I have 6 million data points, 6 million numbers. That's what's going to go into an example, a prediction of an example. I have to somehow process all the 6 million points. Maybe there's 6 million slopes. I don't know what it is, but they're multiplied by different things. And then at the very end, we get a prediction. So that's like kind of at a high level, how we could try to do predictions with images. So any questions there? No? Questions, thoughts, concerns with this approach? It seems like it might take a long time, right? Like if I have 6 million numbers, I mean, we haven't really even had a data set that size in Data 8 yet. So it's a lot of data. But you know, hardware has advanced, your computers are really powerful now. There's a lot of things that we can do to process these images. But let's go through like a little bit on how this predictions actually work here. So at a kind of very high level, we can think of it in the exact same way. Our prediction is going to be a function of some set of slopes and some inputs, in this case, pixels. So in this case, though, X is like millions of RGB values, and then M is millions of slopes, oftentimes called weights. So as we start to move more into like machine learning, and especially like computer vision, we'll start to call these slopes weights, but it's pretty much the same exact thing. But that's essentially what's happening here. So like if you can, in Python, again, write an equation for how we make a prediction based on a bunch of slopes and a bunch of pixels, if I can write them to a function, I can just go ahead and hand off this function to something like minimize, and it will find the optimal values of all these slopes. Now in this case, we have like millions of them. And so that optimized function will take a lot longer to run. So, you know, when we ran it in some examples, like with the nearest neighbor one, it runs pretty quickly. Or if we did minimize a few weeks back with the regression examples, the minimize runs like basically instantly because your data, you don't have that many data points. Your inputs are only like 2 or 3 things at most. But in this case, we have like millions of things. So something like this could take like days, hours, even weeks to actually come up with the result. And so that's typically why we start to call this like training or like training the model, because it actually takes time. And so like for the work that I was doing in autonomous driving, like it would take like over a week, sometimes a couple of weeks to actually train and find the optimal value of these slopes. For my startup, it's the same thing. It takes us about a week right now to train this. So it takes a long time. These images are really big. And remember, 6 million is just one image. Imagine you have like thousands and thousands of images that you want to train, because you wouldn't have like all kinds of different examples of dogs and fried chicken. It's a lot of images. So it starts to get kind of crazy. So, but at a high level, that's basically how it works. Now, if you're curious, I thought I'd share a little bit on how this actually works in computer vision and machine learning. There's some kind of slight nuances with the way it's done with images. So, instead of just taking like millions of pixels and just like multiplying each pixel by a slope, it turns out there's actually a much better way to do it than that. And so to give you a little bit of context of how this works, let's say like in an autonomous driving case. So in that case, you might have like a camera on the front of your car, and you need to detect like whether this thing in front of you, is it a car or is it the road? Like, what is it? Is there an object in front of me? And similar kind of principle applies. But in that case, it'll look something like this. So initially, you'll have an image that's coming in, and maybe it's an image of a car in front of you. And then these pixels are being multiplied by weights, slopes, same thing. And then eventually you get a prediction, like, is this a car or not? Now, one thing that's slightly different is today in kind of like the greatest machine learning, there's this interesting like pattern and layers of all of these slopes. And you don't need to worry too much about that right now, but basically it's just like, there's kind of like a hierarchy, and there's like multiple levels of math that happens. But really you can still represent it all as like a really big equation. It's just gonna be a really big fancy equation. But it's actually just like a bunch of additions and multiplications, and it just becomes this really big equation. But that's kind of how it works. And then that was like the initial approach was like, let's just take the pixels, multiply by these like sequences of weights and slopes. But then somewhere along the way, like around the 60s, 70s, this idea came about of like image-based features, which are like intermediate aspects about our image. And so these were determined by a computer vision expert. And so they were like extracted. And so, for example, the analogy here is like the case that we saw with the oncology example, the science competition, right? There were images of these like cells, right? They're like benign or malignant. And some oncologists came in and said, okay, I can look at an image and I can tell you what is like the uniformity of the cell size, what is like the variance of the cell size, all this stuff, right? So you had an oncologist look at an image and simplify it into like features that are actually important for prediction. So that's what happened here was computer vision experts came in and said, okay, you don't actually need to worry about this whole image. We can extract interesting features about the image. So in this case, like if it's a car, an interesting feature could be like a tire. Like the presence of a tire, that's an interesting feature that we should be looking for. A window, that's something interesting. If it's a dog, maybe it's like the eyes of the dog. Those are interesting features about this image. And so it's actually those features that should be used in your model rather than the original image itself. And so that was like how computer vision originally was used. You'd take an image, you'd have a computer vision expert come in, maybe write some algorithms to extract these important features, just like the oncologist did with those pictures of the cells. And then it's those features that are actually going to have their own slopes and all that. So that's kind of how things start to progress. And then the latest version of these machine learning algorithms, which are called convolutional neural networks, don't worry about that phrase. But basically what they do is the models will actually learn what features are important. So they've basically taken the computer vision expert out of the equation now. And the model will learn on its own what features of this image are important. So it'll learn like, when I tend to see something that looks like a tire, that tends to correlate with seeing a car. If I see something that looks like a tail and 4 legs, it tends to be a dog. So it's kind of interesting, but that's kind of how advanced this has become now, that like, you don't even need the computer vision experts anymore. This hasn't happened yet in other domains, such as like radiology. You still need the radiologist or the oncologist, but could happen eventually. But it's kind of interesting that specifically with like image data, this has happened now. And so like your model is actually able to learn what features are important and like how important each one is relative to like predicting a particular thing. So anyways, that's a little bit of an overview of how this works. If you take additional classes, you'll kind of see how this is all like actually built up, and you'll get to code your own neural network that's like a lot more sophisticated than this, and you can actually do that right here at Berkeley. So it's pretty cool. Anyways, I encourage you to try out and go into this field. Cool. So any questions about any of that so far? Yeah. Is it the same method as the slopes and pixels that picks out the tires and the curves and all that? Yeah, it's kind of similar, but like it's just it's like a it's still the same operations. Like you're still adding and multiplying, so the equation looks pretty similar. But there is one like unique thing about images where it's actually like a set of pixels that's like scanning over the whole image, and so it's like looking to see like, are there any tires in this image at any point of the image? So it's kind of interesting, but that's like part of what happens. So you're like scanning the image for the feature essentially. And so the math is actually the same to do that, believe it or not, but you just write it in a different way, and the data is structured in a different way. It's like basically like a table of data rather than just like a single column of data. Yeah, exactly. So like the tires could be all in different spots across different images, right? Like, and then same for like if I have pictures of a dog, right? Like I could have some pictures the dog's looking straight on, could be looking to the side. So you don't want to be like too specific to a specific pixel. It's more about like the actual shape and the features of the object that are important. So that was like the big breakthrough that happened, was like, let's stop worrying about individual pixels. Let's worry about shapes and like scan the entire image for shapes. That's kind of where the field's developed now. Yeah, so it's kind of interesting. It's pretty clever and it works really well. Yeah, great question. Any other questions? Yeah. Yeah, you can just do this in Python actually. So you can train all these models in Python. That's literally what. So I was at Tesla before. That's literally what they were using, and for my startup, we're using Python as well. So it's all just Python. There's a specific library, just like we have like a data science library. We have NumPy. There's a library called PyTorch. There's several TensorFlow, several libraries that are used for this, but it's all just Python. You do need usually like a pretty beefy computer to do it. I'll talk about it in a bit, but you do need some like big graphical processing units. If you have like a gaming computer and into gaming, you already have this, but you do need some heavy processing to do it. Yeah, it's all you need is Python. Yeah. Oh man. Is there a way to know the ideal amount of training data you need for a data set? It's that's a really tough question. I think there's like a lot of research still happening there. I think it's pretty similar to like how to choose the best number of neighbors. It just varies by problem. It's so hard to know going in, but you know, get as much as you can. Start with something, and then like start with something that's reasonable. You know, I think like the way to think about it. So for example, I'll talk about this in a bit. Like for my startup, we didn't have that much budget, that much funding. So we had to think about how could we get some data initially, how much did it cost to get that data? What accuracy did we get? And then from there, you kind of reevaluate. It's like, okay, it cost us this much to get this much data. Now we might to get maybe this much more. You know, you can kind of start to budget it that way. But oftentimes you're going to have some constraints, whether it's a research project or like a business project. Like you have some funding constraints, but you just kind of start somewhere and then kind of go from there. But yeah, really important to understand how much it costs to get data though, because that's changing constantly. Yeah, really good question. Um, any other questions? Okay, cool. So yeah, how do we actually train this model? Again, this is like exactly what I've already shown you before. All it is that you have a slightly more complex function. So kind of modern machine learning for computer vision, specifically like images, is basically you have a random set of weights and features. So random set of weights over here and a random set of features. So actually your features are not even, they're like initialized, they're just like random numbers, like it's just random noise. But you put it into a structure, into a formula that's gonna make it predict well, eventually. And then basically you just make a prediction with that initial set of weights and features. It's probably gonna do a terrible job first time around because you just initialize it with random values, but you go through and run it on every training example. So in this case, run it on every image, see what predictions you get. You're probably gonna get most of them wrong, or maybe it'll be like 50-50, you'll be like flipping a coin. So it's like kind of a useless prediction. Then you calculate the training error across all the examples, adjust those weights and features a little bit, keep going until the error stops repeating. Now, this might seem like kind of ridiculous that if I have like millions of weights and features, like if I just tweak them a little bit and try it again, this might take like years to actually find the best example. So the good thing is you can use things like calculus to actually like be more clever about how you actually change these. Like you can change them in a particular direction that you know is going to actually improve the accuracy. So there's like other things that you can do, again, all in Python. And a lot of this is just, there's a lot of research just on that, like how do we actually even tweak these weights and features. So, but yeah, it still takes a while even with that, but thankfully it does not take like years. But if you were just literally just randomly moving them up and down, it would take you like years to actually find anything useful because that's just going to take forever. So anyways, that's how it works. And then, yeah, this is like how we typically train. So this is a computer with 4 really big GPUs in them. So if you're not familiar with GPUs, if you have any friends who like play video games, they probably have a computer with some GPUs in it. Graphical processing units. So these are like specifically optimized for like processing images. They were used for video games to like render images. Like when you're playing a 3D video game, it's like rendering a bunch of stuff in real time. So it's like doing really complex math to do that and render this whole world for you in 3D. But turns out these are very useful for training machine learning models for images as well, because they let you parallelize things. So if I have a lot of pixels, I can actually like do the computation on the pixels in parallel. And you know, if I have a bunch of features that I'm trying to like scan over, I can assess each feature in parallel, you know, so there's like things you can do that just like rapidly speed up the progress. And there's like so much innovation happening right now on the hardware side here to like make this process even faster, which is really exciting because again, this is going to benefit all domains and all fields eventually. This whole idea of processing images, it's going to go to everything. You know, I know like a third of the class is like public health, so while this may not feel relevant to you right now, but like it will get relevant to your field eventually. So it's pretty exciting. Cool. So yeah, with that, I just wanted to go through like a few examples of actual problems in prediction and how do we actually like collect the data? How do we actually train it? Just some like real world practical examples. Wanted to share some interesting like findings. So yeah, so the first one I wanted to share was scene categorization. So I think I showed some screenshot like this in one of the lectures last week. But basically, if you're driving, you need to understand the world around you. I need to know like, where is the road? Where is stuff that's not the road? I need to not hit the stuff that's not the road. And so the way you can kind of try to approach this is if you have an image, it'd be really nice if I could build a model that could tell me what each pixel corresponds to in the image. So I need to know that all these pixels are street, all these pixels are a car that I should not be running into. These pixels are a sidewalk that I should not go over, you know. And so as a human, this is all very intuitive and obvious to you, but we need to explicitly have a model tell us this. And so how do we actually go about this process? So the first step is to collect a bunch of data. So good question, kind of segues into this. So we have to go collect a bunch of examples. So we need lots of examples of images of what this car is actually going to see. And so when I was at Tesla, this was really easy for us to do because all the Teslas have have cameras all around them. Every Tesla has like 8 cameras around it. And so we just got customer data. So the customers driving all around the world, we just got all their data. So just driving through all these different roads, and this allowed us to get like a very nice diversity of like streets, lighting conditions, different kinds of cars. You'll see all kinds of weird cars in the world. It's actually very valuable to get that really diverse data. And that's basically how we got the data. And then the next step is, okay, once you have like an actual data set, the next thing is you need to actually annotate it or label it in some way so that your computer knows what it needs to predict. So you actually have to go through every single image like this and then label by hand what each pixel corresponds to. And so you need like a team of people to actually label this. A lot of this has become like kind of semi-automated at this point because a lot of these problems have been solved by so many people. But if you're working on like a brand new project that there is no data for like out in the world, then you have to actually label it yourself. And so this can be super tedious, super manual. It can take a very long time, but a lot of research is being done to improve the process. And these labels need to be really good. Like they need to be pixel perfect. Otherwise, your model is going to make mistakes because your model is going to reference this as like the truth. And so if this is off by a little bit, it's going to affect your model's accuracy. Yeah. Yes, 100%. So anytime you've done a CAPTCHA, you've done data labeling for somebody. Yeah. So yeah, before CAPTCHA used to be like text, I guess, and they'd have like these old textbooks and you just say like, what's the text in the image? So that was actually a big effort to like automatically kind of capture like all these old textbooks and convert them, like digitize them. So that was kind of nice. Now you see these ones where it's like, you know, where's the traffic light or like, where's the motorcycle or whatever. You're basically labeling data. Um, so yeah, a lot of companies working on self-driving. No one's really built a solution that everyone's using yet. So it's been like a couple of decades. They're still going at it. Hopefully soon. Um, but yeah, that's basically what it is. And so with CAPTCHA, it's not like as precise because you're just kind of like clicking boxes. But you do need to have it like really precise, actually, like to the pixel level. You need to know like, exactly when the car ends and the street begins because you want your predictions to be as good as possible. So that's kind of how that works. Once you have your labels and you have your data, labels is basically like the class in this case. So if I have my column of my class, I have my column of my inputs, which is like all the other attributes, the other features that are going to go into the model. I have everything I need then. I have all the ingredients to actually go and train a model. And so then you go through the motions of like, you know, writing out the equation in Python to do this, and then actually going through that iterative process on a machine like this, finding the optimal values of all the various parameters. And then you can kind of be, you know, pretty confident that like once you get a good model, it's going to perform pretty well. And you can go like test it out on test set and evaluate the accuracy and all that stuff. And then finally, you can go and make predictions. So this is an example of the output of a model making predictions. In this case, this is just a simpler model where it's just like predicting whether it's a car or a bus. That's a similar idea. So this is like outputting not only whether it's a car or bus, but it's also like a confidence score of like how confident we are it's of that category. And so you can do things like that too. So that's just an example. So that's one problem. Another problem, which I specifically worked on, was depth estimation. So if you've ever seen the Tesla like screen that's there, the big screen that's there in the middle, it has this visualization that shows you like all the cars around you. So that's the project I worked on, which was how far away are the cars. So like it's one thing to know like that there is a car there, but it's also very important to know how far it is. How much time do I have? Do I need to slow down now? What's the speed of that car? Is it going towards me? Is it moving away from me? In which case I don't need to worry about it. All that stuff, very, very important. So we built a really cool novel approach to do this. Traditionally, you need really fancy sensors to do this. So you need something like a radar sensor to actually like figure out how far away this car is. That's what like a police car is going to use to try to figure out your speed when they're just like sitting on the side of the road with a radar gun. So they're basically like checking to see how fast you're going. But that's typically been the best way to do this. But radar can be like expensive and it's like another part that you have to add to the car, which like adds more to the manufacturing cost, which makes the car more expensive. So if you can find a way to do it just using cameras, you simplify the problem, you decrease the cost of the car, you increase reliability and so on. And so that's what we worked on. So we actually have this really cool patent that we got published about this. You can check it out. It's very interesting. But I'll go through the steps of like how we actually built this model. So the first step was to collect a bunch of data. Again, just like the last problem, this is really easy for us to do because we had a bunch of cameras of people driving all around the world. So that was easy. The next part, which is a little bit tricky, was how do we label the data? So if I have an image like this, am I really going to hire somebody to go through and like write down like, oh, I think that's like 18 feet away and that's like 27 feet away. Like that's not going to work. That's not going to be accurate at all. So this was not an option. So labeling by hand was not an option in this case. So we had to do something a little bit more clever. And so what we ended up doing was the Teslas that were made before like the end of last year, they all had radar on them actually on the front. And so we took that radar data, we like fused it together with the image and we automatically labeled the data. So we basically had the radar label the data for us. And we were able to build a model that was like accurate enough that you could eventually just remove the radar from the car. And then you also don't need radars on like the sides of the car because the same approach is actually able to work for the cameras on the side and on the back. So even though we had radar just on the front, we were able to use that to automatically label the data. So it's kind of an interesting approach and it worked fairly well. So that's kind of how I did that. But yeah, so this is how we like label the data. Once we have the data labeled, from there, training exactly the same. And then making predictions, this is how it looks. So if you're actually driving around, this is actually from Tesla's autopilot system. It's putting these little numbers on each one and it's updating in real time as you're getting closer. And so it's actually able to make these predictions in real time on each image. And so this actually was pretty huge effort and it not only like helped save some costs on the car, but also actually improved the ability to like stop for cars that are stationary in front of you. It just improved the vehicle safety by like tremendous amount. So it was a really cool project. But yeah, that's just like a really cool example also of just using machine learning to make kind of like a better experience. Cool. Any questions about that example? Cool. All right. Last one I wanted to share was from my startup. So I have a sports startup actually that I run. That's actually my main job. So I want to share a little bit about this. So for my startup, we're focused on automating officiating for sports. So imagine like if you're playing like baseball or basketball or something, there's usually a ref there that's like keeping score. They're tracking penalties, they're tracking like balls and strikes in a sport like baseball. So is there a way that we could automate that? Could we bring the cost down for that and make it accessible to everybody and get like professional level officiating? And so that's what we're trying to build. And we're trying to do this all just using your camera. So imagine you could just set up your iPhone on a tripod or something, and it could automatically call balls and strikes for you. So that's kind of what we're trying to do. And so we're focused right now on racket sports initially, trying to go to other sports eventually. But in a sport like tennis, this is what we're doing. So we're trying to build something where it could automatically call the ball in or out, which is a really big problem. Even in like Division I tennis, like UC Berkeley playing Stanford, like the players are calling the ball out themselves, which is like a massive problem. So we're trying to see, can we automate that? And can we also automate the scoring as well? So like, just remove like the need for like a really expensive, umpire or some sort of system to like do this? And can you do this all just using your iPhone? So that's the approach that we're trying to do. And so we started this a few years ago, and the first thing we had to do was collect a bunch of data. So we had to go through and gather a bunch of video footage. Now, this was really hard for us because unlike Tesla, we didn't have a bunch of footage and a bunch of customers already. So what did we do? Well, one thing we did was we went around the Bay Area and just like recorded a bunch of people. Another thing we did was we just scraped a bunch of video from YouTube illegally. Or not illegally, but just like without people's permission. So like this is like a video of like Serena like warming up for like a professional match. So we just went and just scraped a bunch of data from like YouTube. So that allowed us to get like a bunch of video footage. And so these are some of like the scrappy things you might have to do if you're a startup. So you have to kind of like collect your own data from scratch. There was no like just data set we could find online that from some paper that somebody wrote. We had to go collect our own data, and we're going to have to do this for every sport that we go into probably. But those are some of the like things that we tried. And then once we got that, the next thing was, okay, how do we label this data? So are we going to go through and like watch every single video and like record the score and like what's happening? Like that seems really hard. And so what we did was something a little bit clever, I think, which is we made an app that you could use to record your footage. And then we made a companion app that on your Apple Watch, you could keep score. And so basically our customers are labeling data for us. So similar to the CAPTCHA model, I guess, but in this case, it's actually providing value to them. They're actually keeping score and like able to see the score. And so this ended up being a way for us to get like some data automatically. And so that's how we're able to like annotate our footage. And so we don't have to actually like watch all this footage and like keep score, which would take forever. We could just do this. And similar approach we're hoping to try with other sports eventually. And so once you have that, you have your data. In this case, it's video footage. It's not just images. You have the labels. Now you can put it all together. You can train a model and you can make predictions. And so now the app is actually able to tell you the score. So if you look up here, the score is going to change at the end of this rally. And so this is right there. So it just changed. So it's able to kind of keep score for you, and it's able to call the ball in or out as well automatically. So hoping to bring this to additional sports, but another kind of interesting example of using machine learning with images. So last thing just wanted to mention was like some interesting challenges that we came across. And I think these are things that you'll probably run into in like any sort of machine learning context. It's really funny, like a lot of the fancy math and everything has already been solved for. Like a lot of these crazy equations for these models, there's so many papers online, you can just kind of use what's already available online. A lot of the creativity in like solving your problem is going to come from the way that you actually collect your data, the way that you choose to label the data, the way you choose to represent the data. So I'll just share a few examples about that. So one problem we had with the self-driving case was a common thing you might want to do is if you had this image, you might want to have your model predict sort of like the extent of this object using like a rectangular prism. This is just a really common thing that you do because I know this thing's like essentially a rectangle in real life in 3D. And so if I wanted my model to predict like all these corners around this car, I could have it predict kind of 4 points on the top of the car and 4 points on the bottom of the car. But the issue is that these 2 points aren't usually visible. And so even if I have this image and I give it to somebody to label it, it's really hard to label those 2 points, especially the bottom one. It's going to end up being like super noisy because it may not be very consistent. It's kind of hard to actually like accurately label it every time. And so what we found was when we did try to do this and we had people label it, it was just so noisy. The prediction for these 2 red points was like really, really bad. And it was like jumping around a lot. And then what we ended up realizing was like, actually, we don't need those 2 points at all. In order to drive the car, I only really need to know like these 2 points and maybe this 3rd point. That's it. Like, those are the main things that are important. This 4th point on the other side of the car is actually completely irrelevant for driving. It doesn't matter where that point is. So we ended up simplifying the problem and removing that. And so that was a case of kind of, choosing the dimensionality of your predictions. Basically, like, how much are you predicting? What kind of fidelity are you going to choose? It can actually make a big difference in like the kind of accuracy you can get. And you just want to be practical and like choose, like, and generally you want to choose the minimum amount that you need to get the thing done that you're trying to achieve. Anything extraneous is just going to add like additional computation, add potentially additional noise. So I thought that was kind of interesting finding for us. Another one was also just the way that you represent the points. So this is what we ended up settling on. So we said, okay, for every car, we're going to predict 3 points on the top, 3 points on the bottom. But then we realized, what happens if this car now moves into the middle lane? So if it's on the right side right now and it moves to the middle lane, now we just have 4 points. So we went from 6 to 4, but my model is trained to always predict 6 points. So like, how do we deal with that? Is this point corresponding to this one? Like, is this always the left point no matter what happens? Is this one always the right one? Like, how do we deal with that? And then what happens if from the middle it now goes to the left side? So now it's like all the way over here. Now I have 6 points again. So like, how do I deal with that? How do I deal with kind of making sure my labels are consistent? Because your model needs to understand like consistently what's happening. So what we ended up doing in this case was we came up with a rule that like the back of the car that you can see will always be this side. You'll always have like 2 sides for the back of the car essentially, and then there'll be like an optional 3rd side over here. So that was like something that we ended up doing. So it's just like small things like this actually that can have a really big impact in the accuracy of your model. If you didn't have this consistency in how you're labeling it, this model would really struggle to actually train properly, and like you would end up with pretty bad accuracy, or you just have like weird scenarios where the predictions just do like really weird stuff. So it's just some of these nuances of these models. It's just important to be like super consistent with the way that you're like making predictions. Cool. All right. Well, I guess it's pretty much the amount of time we have. Any questions I can answer about any of these? Yeah. Oh, yeah. The question was for the tennis example, how'd you sync up like the scoring on the watch with the video? So, you have like timestamps on both. There was a little bit of human labeling involved to label like each shot. And so we knew it was like the last shot within that point. And so that's kind of how we were able to figure it out. So it's a little bit of, there's still some human labeling involved. So you can't totally automate it. But I guess like the hardest part was automated there. Yeah. Good question. Any other questions? Cool. Awesome. All right. Thanks, everyone. We will see you on Wednesday for the last lecture.